Alrighty, today we're looking at exercise 17b, which is the exact distribution of the sample proportion. Now, again, for this you're going to need to build upon some previous knowledge from previous exercises. So it says here, when we're sampling from a small proportion, and again, they'll use this one often during this particular chapter. It says here, suppose we've got a bag containing 6 blue balls and 4 red balls, and from the bag we take a sample of 4. It says we're interested in the proportion of blue balls in that sample, and it says here we know that the proportion, or the population proportion, is equal to 6, 6 of the blue balls out of the 10 in total, which simplifies down to 3/5. And so you can say in this particular case that P is equal to 0.6. Now, when you go to calculate those associated probabilities of those possible values for the sample proportion P hat, they can be calculated either by direct consideration of the sample outcomes or by using our knowledge of selections. And if you are unsure about selections, you might have to go back and watch a video on that, and I'll put a link up the top. So it says here, example number 4, it says a bag contains 6 blue balls and 4 red balls, which we were speaking about. It says if we take a random sample of size 4, it says what is the probability that there is only one blue ball in the sample? So that is the P hat is equal to a quarter. So there's a few different ways you could go about it, and the first one here, it says you could consider selecting the sample by taking one ball from the bag each time without replacement. And so favourable outcomes in this particular case, so that you get just one blue ball in the sample. It could be red, 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 blue, blah, 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 etc., etc. These are the possible outcomes. Now, when you go to calculate the probabilities of each of these events, obviously red here, there's 4 out of the 10 possible without replacement. The next one, this red here, is 3 out of the 9 left over, etc., etc., down to 2 out of the 8. Obviously this blue here is 6 out of the 7. Yep, so you can calculate that probability. You are then adding those all together and we get 4 out of 35. Method number 2 is again using that selection stuff that we spoke about at the top. It says in total there are 10 ways, or 210 ways to select 4 balls from 10 balls. There are 4 C3, which is 4 ways of choosing 3 red balls from 4 red balls, and there are 6 C1, or 6 ways of choosing 1 blue ball from 6 blue balls. And therefore you can run the calculation of the probability of obtaining 3 red balls and 1 blue ball as follows, which is 4/3. Now again, once you've got that happening, you could come up with the following table. And this table here gives the probabilities of obtaining each possible sample a proportion, P hat, when selecting a random sample of size 4 from the bag. So again, number of blue balls in the sample could be 0, 1, 2, 3, or 4. It says here the proportion of balls in the sample, which is P hat. Again, if there are 4 possible blue balls in the sample, 0 out of 4 is 0. If you choose 1, it's 1 out of the 4. This is 2 out of the 4, which simplifies down to half. 3 out of the 4, or 4 out of the 4, which simplifies down to 1. So that's just the proportion of blue balls in the sample P hat. Again, you could get those calculations for the probability by actually working each of them out, like we did with the previous example. So where you got 0, and they've run these calculations here. So you get a table with these probabilities in it. It says here we can see from the table that we can consider the sample proportion as a random variable big P hat, and you can write the following. So probability of getting a big P hat being equal to 0 from the table is 1 out of 210. They've done that for each of these others here. So probability of P hat equaling a quarter, 24 out of 210, and so forth. Yep. It says here then the possible values of P hat and their associated probabilities together form a probability distribution for the random probability or random variable big P hat, and that can be summarized by this part of the table here. So the proportion of the blue balls, so the P hat, here it is here, the proportions, and here are the probabilities. Yep, so it can be simplified down. It says the distribution of a statistic which is calculated from the sample space or from a sample, such as a sample proportion, has the special name, and this is called sampling distribution. Example number 5, it says here a bag contains 6 blue balls and 4 red balls, and it says using the sample distribution in the previous table, so this one here they're saying, it says determine the probability that the proportion of blue balls in the sample of size 4 is more than a quarter. So here, setting it up, probability of the proportion of the size 4 being more than a quarter. If you look at this table, for it being more than a quarter, it's going to be this one here. So the half, probability of half, plus the probability of the 3/4 and the probability of 1. Yep. So getting each of those, we write down the values here. It's 90 out of 210, 80 out of 210, and 15 out of 210. Simplify things down and we get 37 out of 42. Perfect. Alright, the next part is sampling from a large population. So it says here generally when we select a sample, it's because the population's too large and it would take too long to be able to do that, or too difficult to get that, or just be too much to count. When the population is so large, we assume that the probability of observing the attributes we're interested in will remain constant with each selection, so the sample, irrespective of the prior selections for the sample. So here they're saying, suppose we know that 70% of all 17-year-olds in Australia attend school. So P is equal to 0.7, 70%. It says we will assume that this remains constant for all selections for the sample. Now it says here, now consider selecting a random sample of size 4 from the population of all 17-year-olds in Australia. It says this time we can use our knowledge of binomial distributions, which we've looked at in the past, to calculate the associated probabilities for each possible value of the sample proportion p hat using the probability function. Yep. So this is the probability function. Success was 0.7. Here is not successful, so one takeaway 0.7, which is the 0.3. Obviously here the sample size was 4. Yep, and we've done this before with binomial distributions. And so again, with sample size 4, it could be 0, 1, 2, 3, or 4. You can plug those into this here to get the corresponding values. Indeed, if you put the 0 in here, you get probability 0.0081. You can get each of these as follows in the table. Again, simplifying this down, we're just looking at the proportion at the school and the sample p hat, this one here, and also the probability, and writing it out as follows. So the population that the sample of size n equals 4 is being taken from is such that each item selected has a probability of p being equal to 0.7 of success. It says here, thus we can define the random variable big P hat being equal to x over 4 because of the sample size of 4. Yep. So where x is a binomial random variable with parameters n being 4, so it was 4 in size, and p was 0.7, you can write out the table as follows. Yep. So notice here, like we said, p hat being equal to x over 4, and then writing out the probabilities as follows. Cool. So it says use the sampling distribution from the previous table to determine the probability that in a random sample of 4 Australian 7-year-olds, the proportion attending school is less than 50%. So again, here is 50%. For it being less than this, it's either going to be this category here, this column here, so 0 or 0.25. Get the probabilities of each of those, add them together. We've got the answer there for that. Last thing I want to talk about is the mean and the standard deviation of the sample proportion. It says here, since the sample proportion, which is big P hat, is a random variable with the probability distribution, we can determine values for the mean and the standard deviation as illustrated in the following example. So it says here, example 7, use the probability distribution to determine the mean and the standard deviation of the sample proportion, so big P hat from example number 6. So here are the values from example number 6. What we can do is we know that to calculate the mean, um, it's multiplying each of these together and summing them. So that was from earlier chapters as well. So 0 times this here, 0.25 times that, added them together, we get 0.7. Next, to work out standard deviation of p hat is just the square root of the expected value of p hat squared, take away the expected value of p hat all squared. Yep. So we just worked out this one here, the expected value of p hat. So we've already got this part here in the brackets. We just need to work out now the expected value of p hat squared. So again, squaring each of these values, 0 squared multiplied by its probability, and sum them together. We get 0.5425. So we've got the expected value of p hat squared, which is this part here. To work out this here, it's the 0.7 squared. Yep. So plug these in and we get 0.2291. Perfect. There are some additional rules, and it says here, if we are selecting a random sample of size n from a large population, then the mean and standard deviation of the sample proportion, big P hat, are given by the following. So the expected value of big P hat is just equal to P, and the standard deviation of big P hat is equal to the square root of P multiplied by 1 take away P over N. So there's some simplified formulas here to do this. It says here the standard deviation of sample statistic is called a standard error. So example number 8 says use the rules just that we had above to determine the mean and the standard deviation of the sample proportion big P hat from example number 6, and it says are they the same as those found from example number 7. So again, as we've said here, the expected value of big P hat is just equal to P, which is 0.7, which we said at the start P was 0.7, and from the previous example we worked it out, it is 0.7. That checks out. Standard deviation of big P hat is equal to this here. So plugging in the calculation and running it, we get 0.2291, which is the same as what we got from the previous example, example number 7 as well. So it can be a lot quicker to do it this way. Yep, using those rules. Alrighty, last one. It says here, example number 9. Suppose that 70% of 17-year-olds in Australia attend school. If a random sample of size 20 is chosen from this population, find the following. It says find the probability that the sample proportion is equal to the population proportion of 0.7. So what we need to know for that is if the sample proportion, which is little p hat, is equal to 0.7 and the sample size is 20, then the number of students in the sample is going to be 0.7 times the 20, which is 14. So again, to get work out what the probability of this is going to be, which is here, we plug this into the selection formula and we get 0.1916. Next says find the probability that the sample proportion lies within one standard deviation of the population proportion. So again, we can work out the standard deviation of big P hat. Plugging into this formula here, little p was 0.7, n was 20, we get the standard deviation is 0.1025. So if you've got you're going down the standard deviation, you're going to have 0.7 take away this standard deviation, which is 0.5975. Adding on a standard deviation, you're going to have 0.7 adding on this, which is 0.1025. Adding them on 0.8025. So we find that the probability is going to lie between each of these here. P hat is going to lie between each of those. The probability of then that value, we then need to, because the sample was 20, we need to multiply each of these by 20. So there, that gets multiplied by 20. That's 11.95. This here is multiplied by 20. Cool. Now again, because these take on integer values, you can't have these decimals here. That's basically 12. That's basically 16. Again, we can run that calculation and we get 0.7795. Last but not least, it says the probability sample proportion lies within 2 standard deviations of the population proportion. Again, we're just doing the same thing, but we're multiplying it by 2 standard, or taking off 2 standard deviations, we're adding on 2 standard deviations. Again, multiplying by 20, and we get these from here. Thank you very much for listening up. Have fun with this exercise. Bye for now.